Okay, hey, we're back with another dynamics video, and let's go to the felt tip pen. And so we're just going to do the example that most of us didn't get to because we were playing with hovercraft. Yeah, if you aren't part of the school, you're probably wondering, how did you play with hovercraft? Well, you'll just have to wonder. Okay, there's the example we did in class. Here's the example we didn't get to. All right, so the scenario that we have here is similar but different to the other example. The first thing we'll do is go ahead and just use component math and get the relative velocity. So we know that we have car A and car B, and car A is traveling at 10 meters per second and increasing speed at 5 meters per second. Notice we're saying they're increasing speed as opposed to saying we're accelerating, trying to make it clear that the speed is what's increasing. So that's the tangential acceleration. And we happen to know in acceleration there can be two different components, almost always is two different components for a particular point. And one is going to be the tangential, one's going to be the normal. And what we're going to have to do for that is break that down into components, and then and so we could find the relative acceleration. But the problem asks for both the relative velocity and the relative acceleration. So let's just do the relative velocity first and then go to the relative acceleration. Now car B is traveling at 18.5 meters per second and increasing speed at 2 meters per second squared. So let's go for velocity first. And I like to use the components. It's a lot easier than trying to use the triangles. And it's especially true with the acceleration, which we'll see. Okay, so I'm going to find first the acceleration of the velocity of A. All right, so just as a note, this is usually what I write first, and I should have written, is that I want to find the velocity of A with respect to B. I know that means that sentence, that equation, is the velocity of A minus the velocity of B, right? The way we like to write it often is to say the velocity of A is equal to the velocity of B plus the velocity of A with respect to B. And that's a good way to write the thing, but here is the way to double check that we're getting them correct. Because we could write it the other way, and then velocity of A with respect to B turns into, if we said velocity of B is equal to velocity of A plus, if we used a plus, then it would be velocity of B with respect to A. I don't want to confuse the point, but there is a definite a relationship. It's who is going to be the reference and who's going to be the reference maybe. So we're going to find the velocity of A. We'll break it down into components, and we'll break it down into our x component of velocity and our y component of velocity. So I guess I'll just distribute this magnitude times there. There's 10 is what the velocity of A, and then multiply that by the cosine of 45 degrees, right? So that's going to be positive, right? So because we have a positive x direction, and we'll give it I hat plus negative sine of 45 degrees, because this is a downward, so it's negative. And once again, of course, we have 45 degrees here. So J. So that's going to equal 7.071 for significant figures times I plus negative 7.071 times J. And if we want to be complete and be careful, we could also put meters per second, put our units in there. And the velocity of B, well, that's really pretty easy. That is simply going to be 18.5 I, right? And then plus 0 J. Now I'm going to write it back over here because sometimes it's nice to have this little arrangement where I take 18.5 I and then plus 0 J. And because I want to find, excuse me, let's see, does this work right here? Let me see. Sometimes they work. Nope, that one doesn't. Sometimes the back of the pen can be an eraser, but this one's not. Velocity of A with respect to B is just going to be the bottom one minus the top one. So we subtract it out and we find it's negative 11.43 I plus negative 7.071 J. All right. And if we were going to give our answer in 3 sig figs, we would go ahead and do it. We also want to probably find it in relative or magnitude and direction. So we do that. We could take the sum of the squares, the square root of the sum of the squares of these two components, and we would find it's 13.44 meters per second. And if we found the angle, and quite often this is what I do, is I say, okay, well, it's going to be negative x direction, so negative y direction. So what we want to do is go opposite. Well, it would be this one right here would be opposite from this angle right here. And so the angle is, it's going to be opposite over adjacent. So the inverse tangent of our rise over run, so it's negative 7.071. Actually, I don't need to make that negative because I'm ignoring the signs. I'm just making a little picture of it for myself, divided by 11.43. And I find that the angle is 31.74. So, and when I report that, I want to be careful and make sure that I always put my quadrant, what quadrant I'm referring to. So this is the quadrant, that's the angle that I've found for there. So either one of those is an acceptable answer for the relative velocity. Now for the relative acceleration for this, it's going to be, let's see, I'm going to give my, I guess I can go ahead and try to fit it in here. Maybe I'll go ahead and erase a lot of this. So it's not going to let me do eraser. It's not an option. Okay, well, maybe try it again. Yeah, it does it that time. Okay, where was it? Erase all on this slide. Okay, great. Oh, that's nice. All right, I didn't even know that feature was there. We're back on the pen now. All right, so I want to find first find the acceleration of A. And I know that I already have it in tangential and normal direction, but it really would be better for me to have it in x and y. So I'll just write this thing out that I know that the components here are going to be velocity of A squared over the radius of curvature times the normal unit vector right here. And so we could find that it's going to be 5 times ET, because it says that it's increasing at 5 meters per second, plus 10 squared, so the velocity squared divided by the radius of curvature, which is 100 here, and that's going to be En. And I happen to know that's going to be 1 right there. Okay, so what I want to do, though, is I want to break this down into x and y direction. So let me draw this over here separately. I think it's going to help us to draw these over separately. That this is going to be my E or T and my En. And we've already kind of done this in a previous homework, but it's worth doing again a little bit. So here are my components right here. I'll put them in another color. And I know that it's going to be 1 is going to be the magnitude here, and I'll try to draw it out maybe with a little bit of correlating magnitude. And I want to turn it into, let me see, I'm going to reserve red here. I want to turn it into x and y. So here you go, or more importantly, I and j. So I go ahead and I'll use red for this, and I want to find it. I want to find the acceleration of A, and I'll start out with the i's. And I'll say, so I'll put a big parentheses here. I want to find the contribution to I from the tangential direction. So I come up to here, and fortunately for me, it's 45 degrees. It would be maybe a little bit more challenging if it wasn't 45 degrees, but it is. So I take that value in the tangential direction, which is going to be 5, and it's going to be positive I, right? And I'll take that to be, well, I'll go ahead, the cosine of 45 degrees. And then I'm also going to have a contribution, but from the normal acceleration, that value of 1 in our case. And so I draw that thing up here, and also, once again, this is 45 degrees. So I can go ahead and take a cosine. But it's going to be negative. So it's negative 1 times the cosine of 45 degrees. And that's going to be my I hat. And now I'm also going to do it for the j. And so now in the for the tangential direction, that's definitely going to be negative. So it's going to be -5, right? Because it's going to be in the downward direction like there. And of course, well, I guess I could go ahead and use the sign, but of course over here, this is also 45. But I'm going to say that, okay, well, it's really this opposite from that 45 originally drew there. So I'll go ahead and call it sine of 45. Just to be clear, you have to be careful with the angles. And then I'll also add in the contribution from the normal, right? And so that's going to be this amount right here from this side, which I can put down over here. And so that's going to be also negative, because it's in the negative j direction, times the sine of 45, just because that's the angle I decided to label. Right? So I put all that together, and I get the angle, and I come up with the numbers. Let's see what they are. I believe it's going to be 2.828, if I'm reading my page the right way, and then plus negative 4.243 j, right? And that's meters per second squared, by the way. Now, that's what we're being asked is the relative acceleration of A with respect to B. So we need the acceleration of B. Well, that's simply because it's traveling only in one direction. It's going, and it's in the I direction. It's going to be a positive. Where'd you go here? I think it's a positive 2. Yeah, a positive 2. I could just read my paper. Plus 0 in the j direction. And I have my acceleration of A with respect to B is simply these two vectors subtracted from each other. So that's going to be 0.8284 I plus negative 4.24 j meters per second. I guess there should be a 3 in there. Meters per second squared. And were I to want to get it into magnitude and direction, I would find that it was 4.32 meters per second squared. And also, I could get the angle. It ends up being like 79.0 degrees. Now, let's see. Did I, Nick, because I have Nick hanging out with me. Say hello, Nick.
Hello.
Yeah. Nick, did I draw for this previous one I did the velocity, did I draw the vectors for that? I don't think I did either. Okay, so let me backtrack and do that. So I'll erase all these on here. So another way to approach the vector math of this, and did I even draw this out on the thing? No, I didn't. Interesting. Okay, so this is sort of like a review as well, is that what I could have done, and I often do with my handy-dandy little ruler here, is I'll align with the angled one, and then I will get a magnitude. So like A is traveling at 10 meters per second, and I happen to have a ruler here that has a nice increment here, and I'm going to go ahead and make this 2 inches, right? So that's going to be like 1 inch per 5, I guess you would say. So I'm really doubling up. You don't care, but that's fine. Okay, so what I need to do now, if I want 18.5, isn't that something along the lines, what's 2 times 18.5? Is that like 37? Am I right about that? Okay, cool. I think... All right, so but that's going to be horizontal. Well, that's supposed to be horizontal. Okay, so this is the velocity of B right here. And here's the velocity of A. And remember that I said that the velocity of, we're trying to find the velocity of A is equal to the velocity of B plus the velocity of A with respect to B. Okay? Well, that's going to form the velocity triangle, as opposed to the one where I want velocity of A with respect to B is equal to the velocity of A minus velocity of B. It's better to rewrite that in these terms. So we take the velocity of B right here, and this is the velocity of A. You'll see that they match up, right? Well, now we want to go make sure that we go the vector math the correct way. Is we're going to add B and AB. So when we add them together, they go head, tail, and then... right to here, right? Oops, come on. So this is velocity of A with respect to B. right there. So what we could do now is if we have, we know this angle to be 45 degrees, and we would be able to take and say, okay, well, the law of sines would let us find what the magnitude of velocity of A with respect to B would be, simply because taking velocity of, can I do that? No, I need to use the law of cosines, right? So I would take like, quite often what I'll do is I'll draw them again separately and call this one like A, B, C, and then that one big A, big B, big C, and I could go ahead and I could use the law of cosines to find C squared is equal to A squared plus B squared minus 2AB cosine of C, right? I could do that. So you could just trust me that I could do that. But here is probably the way that I would not recommend you to attempt to do this problem if it were. Oh, and by the way, I did do it right here. I did do it. Okay, so let me just finish it up right here. Okay, so I would say that VA with respect to B, which is this side right here, squared is equal to 10 squared plus 18.5 squared minus 2 times 10 times 18.5 times the cosine of 45 degrees, and I'd find that VAB with respect to B is equal to 13.44 meters per second, which, if you'll recall from the previous treatment of this thing, was the same magnitude that I found. By the way, that's the magnitude that I'd be finding. And then if I wanted to find the angle of it, of attack right here, I would try to look for this guy right here. So he would be my, that would be my angle A that I would try to find, and I'd use the law of sines. So I'd say the sine of, and I guess I'll use A right here over this is going to be 10 right here, right? Because this is magnitude right here of velocity of A is 10, and equal to the sine of 45 right here, that's this angle, divided by this value that I just had, 13.44. And doing all that, I would end up, excuse me, I don't need that. I'd end up finding that A would be equal to 31.75 degrees, which is really what I would, is what I found in the previous one, right? That I found that the A with respect to B was equal to 13.44 meters per second. And I'm going to try to write this the right way, 31.75 degrees. And I had that quadrant. I believe that's what I found, right? Sure. 31.7 is what I had written down before. All right, so lastly, I want to demonstrate why it would be difficult to do this as a, to do the same problem for acceleration using triangles. Okay, so I know my, I would want to write my acceleration is equal of A is equal to the acceleration of B plus the acceleration of A with respect to B. All right, but each of in the case here, acceleration of A has two components to it. It has normal and it has tangential. So we have to address that in the triangles as well. So what we would do here, if I was going to draw this thing out, was I would take the acceleration of, let's see, I want to use B and I want to plus, okay. So I would take the acceleration of B, maybe, something along these lines right here, the acceleration of B, and I need to add it to the acceleration of A with respect to B. So that would be, that's the final outcome, what I want. So I need to take the component. So I have a component here in the normal direction here. So this is going to be the acceleration of A in the normal direction. And I also have a component in the tangential direction. So moving that over here, that's this guy. And he's a larger component. That's the acceleration of A in the tangential direction. If I wanted to get the total acceleration, of this thing. I'll just switch to red here and say this guy. Now that guy is the acceleration of A, the complete acceleration of A. Do you agree with that?
Mm-hmm.
Okay. So now I can go ahead and I can find these, right? So I went, I need to be able to find this. I end up going, I probably use another color. I don't know. Doesn't matter. Yeah, sure it does. You know what? Okay, so that right there is going to be the acceleration of A with respect to B. And we could kind of see that it's getting closer to that 79 degrees that we didn't find out. I didn't do a great job with my relative magnitudes right here. Because, I think this B should have been a lot shorter. And then you would have seen that the acceleration of A with respect to B would have been closer to that 79, that steep angle. But you could see here that it's really, in terms of the components that are available, it's instead of a triangle, if you use the components, it ends up being a trapezoid. There's examples in the book that show you where that would be really confusing if you laid them out the wrong way. So I really would recommend that you, for acceleration, that you use the component method as opposed to laying out the vectors. Although this, by laying them out afterwards, you could get sort of a sense of what's actually going on. So that this one is the value of 1, this one is a value of 5, this one is should be a value of 2 right here, right? So this should be a shorter vector. Anyway, that's the long and the short of it here. Hopefully this gave you a little bit of help on the homework and pushed you towards doing the component math as opposed to doing the long way around on acceleration to do the vector math.